Welcome to the Chapter 5 Part 1 video. Chapter 5 is about analytic trigonometry, so this is going to be applying the trigonometry and kind of taking it to the next step from what we saw at the end of the last semester. And we're going to start section 1 as fundamental identities. We're going to look at what identities are, which are basically equations that are always true. We're going to look at our basic trigonometric identities, which should be familiar. Then we're going to get into the Pythagorean identities, co-function identities, and odd and even identities. And then we're going to apply those identities. Why are they so important? Because we'll use them when we're working in calculus, but also they can be applied to fields such as physics, statistics, biology, and scientific fields like that. So let's start out with our basic trigonometric identities. We have our reciprocal identities. These should be familiar. In the past, we've kind of taken these as definitions. So the difference just between a definition and an identity is that an identity is always going to be an equation. If you notice, each of these identities has kind of two parts that correspond. Cosecant is the reciprocal of sine, and sine is also the reciprocal of cosecant. So we have three pairs of identities here, and each of those is the reciprocal, as we've defined already last semester. Our second type of basic identity is the quotient identities. And again, we've already looked at these as definitions. So we have tangent is sine over cosine, and then cotangent, which before we looked at 1 divided by tangent, can also be written as the quotient identity of cosine divided by sine. So again, looking at these identities that we've already seen before, but now we can give them an additional name. The next set of identities that we're going to look at are the Pythagorean identities. You might recognize Pythagorean like the Pythagorean theorem. Pythagorean theorem stated, if I have a right triangle, a squared plus b squared equals c squared. And we can say that for any triangle in our unit circle, so we have an image of a unit circle here, our one of the legs of the triangle, the x value, can be called cosine of t or cosine of theta. The second leg of the triangle is our sine of theta or sine of t. And the radius here will always be 1 because this is a unit circle. And so if we take that triangle and we apply the Pythagorean theorem to it, we find that cosine squared plus sine squared equals 1 or 1 squared. And that's where we get our first Pythagorean identity. But maybe we're trying to solve something, and instead of having sine and cosine, we're given one of our other trigonometric functions. So what we can do is we can take that Pythagorean identity, cosine squared plus sine squared equals 1. And remember, in this case, theta would be the angle. In our diagram here, we called the angle t. T, theta, x, whatever variable is inside of our trigonometric function is an angle. So in the diagram, the angle is called t. In the equation, that same angle, whatever the reference angle is theta. So if I don't have sine and cosine, then what I can do is I can divide every part of my equation by cosine squared theta, and I get another Pythagorean identity. So this counts as a Pythagorean identity because it's still coming from that Pythagorean theorem, but now we can simplify to 1 plus sine divided by cosine is tangent, but these are squared, so this is tangent squared theta. 1 divided by cosine is secant squared theta. Okay, now this is one of the ways that you can see this Pythagorean identity. The same Pythagorean identity could also be written, if I wanted to write it as a 1 equals secant squared theta minus tangent squared theta. So notice in our first Pythagorean identity, we had sine plus cosine, both squared. So cosine squared plus sine squared. In our second Pythagorean identity, we have two different ways that we can write it. We can still set it equal to 1, but it would be secant squared minus tangent squared. If we do that same process, but instead of dividing by cosine squared, we divide by sine squared, we get cosine squared theta plus sine squared theta equals 1. Divide everything by sine squared theta. Cosine squared divided by sine squared is cotangent squared theta. Sine squared divided by sine squared again is 1. 1 divided by sine squared is cosecant squared theta. So again, if we want to write this in another format, we can solve for 1. 1 equals cosecant squared theta minus cotangent squared theta. So our third Pythagorean identity can also be written 2 ways. It's up to you which way it's easier to use. We will be using it in both forms. So if I want to substitute, let's say I have an equation or an expression that uses secant squared and I want it to use tangent squared, then we would use the equation that's solved for secant squared. But that's not always how it's going to be. So we have to kind of be flexible with how we use these Pythagorean identities. These are equations, so we can still do any operation that we could do to an equation, we can do to these identities. Okay. So let's try an example. Now, I'm going to split my screen because we've already seen this type of problem and we already have a method that we saw last semester that we could use here. And that is that we want to find sine and we want to find cosine. And we're given that tangent of theta is 3 and that cosine of theta is negative. The first thing that I'm going to do is I'm going to draw my quadrants. I know that tangent is positive, so it can't be quadrant 2 or 4. I also know that cosine is negative, so it can't be quadrant 1, so we know that our angle is in quadrant 3. Okay, so if I draw my triangle here, here's theta, there's my right angle. Tangent of theta, TOA, opposite over adjacent is 3 over 1. So my opposite is 3, adjacent is 1. I need to find the hypotenuse. So I would say the hypotenuse squared, let's call it C squared equals 3 squared plus 1 squared. C squared equals 9 plus 1. C equals plus or minus the square root of 10. This is a distance, so it has to be positive. C is the square root of 10. Then we can also do this now finding sine and cosine from the triangle. So sine of theta, so opposite is 3 over the hypotenuse is the square root of 10. Proper form, we should rationalize. So we get 3 times the square root of 10 divided by 10, which does not simplify. And then to find cosine, so adjacent is 1 divided by hypotenuse is the square root of 10, which is the square root of 10 over 10. To solve this same question by using identities, now we still want to find sine and cosine, knowing that tangent of theta is 3 and cosine of theta is negative, but we're not going to set up a triangle this time. We want to use one of our identities. So if you look back at your notes and you look at the identities, we want to find which identity uses tangent to find another another function that's related to sine or cosine. And if we're looking at those, the reciprocal identities, I can use tangent to find cotangent, but that's really it. If we look at the Pythagorean identities, we can use tangent to find secant. So I'm going to write the identity here. We have 1 plus tangent squared theta equals secant squared theta. But I have tangent, not tangent squared. So I have 1 plus whatever tangent is squared equals secant squared theta. Tangent is 3, so I can substitute that in. So 1 plus 9 equals secant squared theta. 10 equals secant squared theta. But we don't need secant, we need sine or cosine. So now that we have secant, we say, okay, well, which one can we find, sine or cosine? Well, secant is the reciprocal of cosine. So if I find the value for secant of theta, which is going to be plus or minus the square root of 10, we know that cosine is negative. So we can say that secant of theta equals negative square root of 10 equals 1 over cosine of theta. So then cosine of theta equals negative 1 divided by the square root of 10. Okay, so then why is this different than what we had before? And the answer to that is because remember, when we're doing our triangles, we're not looking at distances, we're looking at where they are in the coordinate plane, right? And this is why using identities is often more precise than using some of the methods that we talked about last semester. If we look back at our diagram, this triangle that's in quadrant 3 should have a negative x and a positive y. But we did it 1, 3 square root of 10 because those are distances. And I saw a lot of this as well. That 1 should be negative. Sorry, quadrant 3, y is also negative. I wrote that it's positive. Negative. Negative 3 should also be negative. Now, it doesn't change much with our values, except it changes their sign. This should be a negative 3 and a negative 1, which makes this negative. And it also makes this one negative. That's why we got a different answer here. Not because different methods should give you different answers, but using the identities makes it easier to not drop negatives. So that's one of the reasons that this could be more useful than some of the methods that we've seen before. Okay, so we found cosine, now we want to find sine. And there's a couple different ways that we can do this. We want to use the information given as much as possible. So since we were given tangent, if we can find sine by using tangent, that's going to be the most accurate way. So I have tangent and I have cosine and I want to find sine. Luckily, the quotient identity gives us this relationship. Tangent of theta equals sine of theta divided by cosine of theta, which means that I could say sine of theta equals tangent of theta times cosine of theta. So sine of theta equals, tangent was 3, cosine is negative 1 divided by the square root of 10 equals negative 3 divided by the square root of 10. Now again, we can rationalize those, but notice this is the same answer that we got before with the correct negative sign. Okay, so that mistake that we so easily fell into in our methods from last semester is much easier to rectify by using these identities. Okay, let's take a look at our next type of identity. And for these identities, I want to show you where they come from. So cofunction identities, so sine and cosine, tangent and cotangent, secant and cosecant, right? Those are cofunctions. And what they come from is a right triangle. If I have two angles here, I have angle A, and I'll use a different color here for angle B. So first we want to look at all of these ratios, all of our trigonometric values in terms of x, y, and r for angle A. That's the red angle. Sine of angle A, so opposite over hypotenuse, that's y over r. Tangent, opposite over adjacent, that's y over x. Cosine, so that's adjacent over hypotenuse, x over r. And then I'm going to use those reciprocal identities to find the last three. Cotangent will be x over y. Secant is the reciprocal of cosine, so that's r over x. And cosecant is the reciprocal of sine, so that's r over y. Next, we're going to do the same thing, but this time for angle B. Sine of angle B. So again, so opposite over hypotenuse, but our opposite here is x. That's x over r. Tangent is opposite over adjacent. That's x over y. Cosine, adjacent over hypotenuse. That's y over r. Cotangent, y over x. Secant, r over y. And cosecant, r over x. Now what we want to do with these is now kind of pair them off and say angle A and angle B are complementary angles. And that's where from the co-function comes from. They come from complementary angles, right? So angle A and angle B are complementary. Meaning that they add up to 90 degrees. Okay, and if we look at these functions, sine of angle A matches y over r. So y over r is cosine of angle B. And we have tangent of angle A, that's y over x. Y over x is cotangent of angle B. And then we have secant of angle A, r over x. Well, r over x is cosecant of angle B. So do you see how the same ratio represents the co-function for the complementary angle? Sine of angle A is cosine of the complement of angle A, which is angle B. So what that gives us is it gives us the identity that if I take 90 degrees or pi over 2 minus the angle, that's the complementary angle, then I have an expression that's equal to the co-function. So sine of pi over 2 minus theta, sine of pi over 2 minus theta, that's the complementary angle, equals cosine. That's the complementary function. So this is the complementary angle, pi over 2 minus theta, or 90 degrees minus the angle, is the complementary angle, is equal to the complementary function. Okay, and that's true for any of our 6 pairs of complementary functions. So sine and cosine, cosine and sine, and so on. Okay. Our next identities are even and odd identities. Now, sometimes these are hard to visualize. We've seen this before in a previous chapter, so I'm just going to kind of go through that visualization again of even versus odd. Even means it's symmetric over the y-axis. I'm going to use a parabola to demonstrate this. Okay, for an even function, if I have x and I have negative x, they have the same f of x value. So f of x, this is the y value for x, and f of negative x are equal. F of x equals f of negative x, or f of negative x equals f of x. They have the same height. For x values that are opposites, the y values are the same. So again, for a parabola, that would be like saying 3 squared equals negative 3 squared. Opposite x values, same y values. For an odd function, and I'll use a cubic function, if we do the same thing, if I have x and I have negative x, this time our function values here, f of x and f of negative x. Okay, these are just sketches. I'm not doing these exact. Have opposite values. So let's see. So f of x, f of negative x is the opposite of f of x. So this would be something like 2 cubed is not equal to negative 2 cubed. It has to be negative 2 cubed to equal negative 2 cubed. So negative f of x equals f of negative x. Okay, so how does that relate to our trigonometric functions? Well, if we remember from the last chapter, our trigonometric functions all have this property of even versus odd. So if I sketch these real quick, we can kind of remember that. Sine, like this, is odd, which means that cosecant is also odd. Cosine, like a mustache, is even, which means that secant is also even. Tangent, very similar to cube, except that it's periodic, is odd. Therefore, cotangent is also odd. And so we get these identities that say sine of negative x for an odd value. That negative essentially pops out front. Sine of negative x equals negative sine of x. If I have opposite x values, then I also have opposite y values. Cosine, which is even, if I take cosine of a negative x value of a negative angle, that's the same as cosine of the positive angle. Okay, so we have 6 more identities here relating to whether the function's even or odd. So if I take cosine of 40 degrees, that's going to be the same as cosine of negative 40 degrees. Now we can make sense of this with the unit circle as well. If we look at a unit circle, cosine is our x value. So starting from an angle of 0, as I go around the unit circle in the positive direction and the negative direction, those are going to have the same x value, right? Cosine is the x value on the unit circle. Whereas for sine, if I start at 0 and I go around in the positive and negative direction, those are going to have opposite y values, and the y value is the sine. Okay, so again, we can relate that back to the unit circle as well. Okay, I have here kind of a screenshot of the identities that we used. Handwrite these somewhere in your notes. Don't just print them. You're not going to remember and you're not going to be able to use them as easily if you just print them out. You have to handwrite them. And the more often you write them, the easier this will be. Using trigonometric identities is always difficult, okay? I don't know that I've met anyone that has said that this is an easy section. It will be easier for some people than for others. However, trigonometric identities are hard because it takes a lot of practice, So the more you can write these identities down, the easier it will get. And every time you use an identity, you should write it down. Let's see if we can use one. I have a couple examples here. So the first one, we want to simplify by using the identities. I have cosine cubed x plus cosine of x times sine squared of x, and I want to simplify this. Our goal when simplifying, our goal is always going to be to try our best to write it as just one trigonometric function. So right now we have cosine and sine. We've got 2 terms. How can we simplify this? Well, the first thing I'm going to say is because both terms have at least one cosine. So I'm going to factor that out. So if I factor out cosine of x, what I'm left with is cosine squared x plus sine squared x. I don't have an equal to something. This is just an expression. Okay, but now I have cosine squared plus sine squared. This is one of our favorite identities. I would call it our favorite identity. This Pythagorean identity, cosine squared plus sine squared equals 1, because it takes something that's rather complex and simplifies it very nicely. So now we have cosine of x times Pythagorean identity number 1. Cosine squared theta plus sine squared theta equals 1. So that whole thing just becomes 1 equals cosine of x as our final answer. Notice the identity had an argument of theta, but the given expression was given with an argument of x. Remember that argument is a dummy variable, meaning we could call it t, we can call it x, we can call it theta. Whatever we call it, we can still use that identity. But when I use that identity, I don't change the angle in the expression. So this is not the same as cosine of theta because there was no theta given. Okay, let's try another one. This time we want to simplify an expression given. This is a fraction. I notice in the numerator I've got cosecant minus 1, cosecant plus 1. Those look like conjugates. So what I see is two factors that could be written as a single factor if I multiply them. So I'm going to go ahead and distribute the numerator. So I'm going to FOIL this. Cosecant squared x plus cosecant x minus cosecant x minus 1. Those cancel out as I knew they would. Cosine squared x. Okay, so now I'm going to go ahead and rewrite it. Cosecant squared x minus 1 divided by cosine squared x. Now, I know I have cosecant, and I have a 1. And anytime I have a 1, it should make me think of the Pythagorean identities. Now, this time I don't have sine or cosine. That would be our first Pythagorean identity. I don't have tangent and secant. That would be our second Pythagorean identity. I have cosecant. So this is Pythagorean identity number 3. And our Pythagorean identity number 3 stated cotangent squared theta plus 1 equals cosecant squared theta. But I don't want to replace just the cosecant. I could, that would be fine. I would like to replace the cosecant squared minus 1, because it's that minus 1 that kind of tipped me off that this was going to be a Pythagorean identity. So I'm going to go ahead and solve for cosecant squared minus 1. I'm going to subtract 1 from both sides. So we can replace this now with cotangent squared theta equals cosecant squared theta minus 1. So this gets replaced with cotangent squared theta. It's really just a bunch of substitution. However, now I have cotangent squared theta divided by cosine squared theta. So I'm going to think of this as cotangent squared theta times 1 over cosine squared theta, because I know that cotangent can be written as a quotient. So I'm really just kind of picking this apart and saying, what do I know about each of these trigonometric identities? How can I write this in a simpler way? A couple tips. If you get stuck, write everything in sine and cosine. Okay, sometimes that's going to make it more complicated before it makes it simpler. But if you get stuck, that's a good go-to tactic. Look for 1 to use a Pythagorean identity. Those are a couple go-to strategies. Okay, we'll go through more strategies as we go through the chapter as well. So what I'm going to do is I'm going to rewrite cotangent. Cotangent is cosine squared theta divided by sine squared theta. So I replaced cotangent times 1 divided by cosine squared theta. Now, luckily, those cosines cancel out, and we get 1 divided by sine squared of theta. We know that the reciprocal of sine is cosecant squared theta. I have it written as a single Pythagorean or a single trigonometric function, then I can't simplify any further. Okay. I believe this is our last example here. We want to solve the trigonometric equation. So this time we have an equal sign. We should get a value, x equals something. We want to find all values of x in the interval from 0 to 2 pi. So just the first revolution. I don't want to find, 3 or 4, all the coterminal angles. I just want to find the first revolution. And this is very common because that's 1 cycle around the unit circle. That's all of the angles before they start repeating. So I have sine cubed x divided by cosine of x equals tangent of x. So I'm going to look at this. I'm going to say there's a fraction. I know I'm solving for x. Then I know that cosine of x cannot be 0 because that's a denominator, and a denominator can never be 0. This is a tactic we talked about way back in chapter 2. You don't have to do this, but I do find it helpful. So I recognize that tangent is sine over cosine. So we're going to rewrite tangent of x. Sine cubed x divided by cosine of x equals sine of x divided by cosine of x. Now, whenever possible, we want to avoid dividing by functions, dividing by something with a variable. So instead of dividing, I'm going to go ahead and subtract over the sine of x divided by cosine of x. That way, we're not losing information. Sine cubed x divided by cosine of x minus sine of x divided by cosine of x. So essentially, I just subtracted tangent of x from both sides to get it equal to 0. And now I can start factoring. I have it set equal to 0, so factoring can give, we can use the 0 factor property. So I'm going to start by factoring 1 over cosine of x. That way I don't have to deal with the fractions anymore. Sine cubed x minus sine of x. Okay, well now there's a sine of x that I can factor. Now this is not sine squared of x, right? If I have x cubed minus x, it does not become x squared. Be careful about that. We're not subtracting the exponents here. We're subtracting sine of x from sine cubed of x. Those are not like terms. But now I have 1 divided by cosine of x times, I factor out a sine of x, and I'm left with sine squared x minus 1 equals 0. Okay, well, 1 divided by cosine of x, can't really simplify that. Sine of x, can't really simplify that. But what about sine squared x minus 1? Remember I said to keep your eye out for 1s. Well, we know that cosine squared x plus sine squared x equals 1. So that means if I subtract 1 from both sides and subtract cosine squared from both sides, I'll get that sine squared x minus 1. That's what I was looking for. And that equals negative cosine squared x. So I took something that I knew it had sine squared and it had a 1. I used the Pythagorean identity. But then I rearranged the Pythagorean identity until it looks exactly like what I need to substitute. So that becomes now negative cosine squared x equals 0. Using the 0 product property, 1 divided by cosine of x equals 0. Sine of x equals 0. negative cosine squared x equals 0. Let's start with 1 divided by cosine of x equals 0. When can a fraction equal 0? Only when the numerator is 0. So this is going to give us no solutions. Okay. When can sine of x equal 0? Well, we know sine of x can equal 0 when x equals, let's look at our graph of sine, between 0 and 2 pi. X will be 0, pi, and 2 pi, but we're not including 2 pi because it's got a parentheses. And then lastly, when will negative cosine squared x equal 0? Well, we could answer that, but remember how cosine of x cannot equal 0 because of our denominator? So these will be extraneous. So we had 3 factors that we had to check. We checked each of them, and we end up with our answer x equals 0 and pi. Okay, that's it for this video. We'll have some more practice in class. I won't be there, but you'll have a math Excel to work on. And if you have any questions, you can always email me, and then I will be back on the following class.